Let us now take a look at our final question. And this question's a little bit long, and so we'll take a quick look at it, and we'll follow up and wrap up this question in our VIP session. Here, I want to talk about del and garbage collection in Python. And I want to give you a sense of how all of this works. Let's take a look. Remember, the del statement in Python only decrements the reference count. Outside of very limited scopes, we generally don't know what the reference count of an object is, so we don't know if that del will actually lead to the deletion of something, the freeing of memory, or not. Let me show you an example. If we have this class T, and we implement an init and a del, what some people call a constructor and a destructor, we can see that the init is called as part of the initialization of this object when it's constructed, and the del is called when the object is deallocated, when the object's reference count hits 0. I don't like to use the word constructor and destructor because I think if anything is a constructor in CPython, it's really the new that's really constructing the object, and this is more of an initializer. But whatever the case may be, we have a new, we have an init, and we have, let's implement that, and we have this del. Now, let's pass that in so you can see all three of those steps. Now, this del is called because when the script terminates, it deallocates anything that it allocated and it does any cleanup that it needs to do. But we don't really know when this del method is going to be called. This del method is not called when you do del object. This is called when the last reference to this object is removed when the reference count hits 0. And because you don't know when the reference count is going to hit 0, you don't really know what the timing of this is. And so in general, you can't really use del to implement any sort of cleanup if you really rely on that cleanup happening at any time, at any specific time before program termination. If it happens any time before program termination, you don't care if it happens 1 millisecond before program termination or 1 hour before program termination, it's fine. But if you need to really tightly control that it happens at this specific point in time, you cannot use this del. Because it's not that hard for instances or for references to an object to be captured that prevent this del from being called. When I do del here, I'm just decrementing the reference count. But if there are additional references out there and the reference count doesn't get decremented to 0, this thing will not be deallocated. It will not be cleaned up. Here I have an object which is being captured in a reference to another object. I'm passing it in. What this is then doing is, you can see even after the del gets called, you can see the del doesn't actually do anything. The only time when this del method here on this original class gets called is after the thing that had a reference to it, where it sneakily captured a reference to it, gets deallocated itself. And it's very easy for these references to just kind of be caught. So you don't really know the timing of when this method will be called, and you don't really know what this del is going to do. In general, what you should think about this del is not even decrements reference count. This just removes a name from your scope. In other words, makes a name no longer accessible to be used. You should think of this in the same way that you don't think of import as creating or as running a module. You think of it as making a name available for use. Del is really about making a name no longer available for use. It's about removing a name from your scope because you don't know anything more than that. Now, if it were the case that you're like, well, I kind of know where my references are, I don't think you do, because there's many small places where references can be captured and it's not clear. Like if you had some collection type here, you can see in these two cases it's a very small change from this code to this code. And you can easily see where somebody wrote the code this way originally, and then they decided, oh, you know what, I need to do X for X in data, if X, and here, where they preserve the original container and had a reference to it, here they're decomposing the container, they're iterating over the container, and so they'll remove the reference to the container. In one case, a reference is being caught, which will prevent the del of this from being called until this thing falls out of scope, until this thing gets decremented to 0. In the other case, it won't. And you could think that there's all sorts of implicit ways where you can capture copies or where small changes to your code can or may not make copies. Like here, this makes an implicit copy, and so translating the code from here or changing the code from looking like this to like this, you wouldn't think might have an implication on what's still in scope, and therefore when something gets destructed, when that del gets called. In fact, if you need to control the timing of a sequenced operation, what do? Well, use the context manager. Well, let me show you how this relates to the garbage collector. The GC module in Python gives you the ability to introspect details related to the garbage collector. So you can actually ask the garbage collector what the reference count of an object is. Here you can see the reference count for x is 2 and the reference count for y is 1. And of course I have to explicitly subtract 1 because the function getRefCount adds 1 to the reference count by virtue of being a function that needs to look at some data, that needs to keep that data alive until the function is finished. And so here you can see we can actually ask the sys module, tell us what the reference count of an object is. We can ask the GC module to tell us what the reference for an object is, that is, what is referring to that object, and what the referrers are, what refers to that object. And here you can see in the refers, you see this thing here looks like a dictionary with a mapping from a name to some object. Well, this is just a dictionary of B's instance state. What can you do with this? Well, you can kind of look at some debug stats around the garbage collector and get a sense for how the garbage collector works and whether you're introducing garbage collector pressure. You can see this, the generational garbage collector. But it turns out that there are certain circumstances where you might need to use the garbage collector in order to guide the design of your work. In the VIP session, what we're going to talk about is a really interesting example where somebody tries to implement what's called an attribute dictionary. Some sort of dictionary-like structure where you can use a square bracket lookup or the dotted lookup to access the same attribute. Just like you can do a JavaScript or just like you can do it on a pandas data frame. And the two canonical implementations of it, one from a cookbook that seems to be kind of floating around the internet, and one that is actually works and is a better implementation. And where the implementation is very, very subtly different, but as a consequence of how this implementation interacts with the garbage collector, namely that the garbage collector cannot deterministically immediately deallocate things if there are circular references, and this introduces circular references, you can create memory pressure that will cause a long-running Python function to run out of memory. Whereas in the other formulation, you won't create that memory pressure. In the VIP session, we'll take a look at one way to analyze how much memory is being used in Python to take into account things like the obscurity of how pandas manages memory, as well as the obscurity of how the interpreter manages memory. And a very simplistic technique using the idea of a high watermark to set, this is the high watermark, and does it run under that high watermark? And if so, then my memory usage is okay. If not, how is that changing my high watermark up or down? And we can use that approach to analyze these two examples and to see the direct implication for the long-running memory pressure, the long-running stability of one of these two implementations versus the other. From that, we will derive a general sense of how we can come to terms with Python, giving us the flexibility of not having to worry about memory management, but still requiring that sometimes we have to be a little bit careful about memory management.